Okay, so every single night, our telescopes are getting hit with this flood of mysterious signals from deep space. And you gotta wonder, what are they? Are we seeing dying stars, some kind of weird celestial objects we've never seen before? The problem is, there is just way too much data for any human to sort through. So in this explainer, we're gonna break down this really cool new study where scientists basically trained an AI to do that exact job, to become an expert astronomer. So here's how we're going to tackle this. First, we'll talk about this cosmic data deluge, just how big the problem is. Then, we'll get into reading what they call celestial fingerprints. After that, it's time for training the AI astronomer. We'll see how that works. Then, of course, the AI's report card. See how it did. We'll even look at an early detection test to really push its limits. And finally, we'll wrap up with what this all means, smarter AI, and maybe even better data. All right, let's dive into part one, the cosmic data deluge. So the heart of this whole story really starts with a massive, and I mean massive, problem. We've got these next-gen telescopes, like the LSST, and they're about to unleash an absolute tsunami of data. We're talking more information than any team of humans, no matter how brilliant, could ever hope to analyze. And this forces a fundamental shift in how astronomy gets done. You know the old way? You'd have an expert, or maybe a whole team of them, literally sitting there, manually going through the incoming data. I mean, it's a process that could take days, and honestly, it could be pretty subjective. It was just not built to scale. The new way? Well, it's born out of pure necessity. We have to use AI to automate this whole classification thing. That's the only way to make it fast, objective, and able to handle this cosmic flood of information. Okay, on to section 2, reading celestial fingerprints. So here's the big question. If we're going to teach an AI to be an astronomer, what is it actually learning from? What's the textbook? Well, the answer lies in something called a light curve. This is like the fundamental piece of evidence we get from these super distant objects. So what is a light curve? It's actually pretty simple. It's just a chart that tracks an object's brightness over time. The best way to think about it is like a unique fingerprint for a star, or maybe even its heartbeat, like a cosmic EKG. A supernova, for example, is going to have a totally different heartbeat than, say, a pulsing star. And these patterns, these are the clues our AI is going to learn to read to figure out what it's looking at. And believe me, these fingerprints have their own distinct personalities. First up, you've got your S-light curves. That's the classic supernova look, a big peak and then a nice slow fade. Then you have the fast ones, which are these short, super sharp bursts of light. And on the flip side, you have long ones that just seem to hang around forever. And of course, you get the predictable ones, the periodic signals that just repeat over and over, and then the total wildcards, the non-periodic ones that are just all over the place. The AI's job? It has to learn to tell every single one of these apart. So, who's the detective we're hiring for this cosmic mystery? Well, the researchers picked a very specific kind of AI. It's called a long short-term memory network, or just LSTM for short, and it's basically the perfect tool for this job. Why? Because its whole reason for existing is to find and remember patterns in data that happens over time, which is exactly what a light curve is. All right, part 3, training the AI astronomer. This is where the fun really starts. Think of it like a training boot camp. Before our AI detective can go out and start solving cosmic cases, it needs to go through some serious training. And that means taking all that messy, raw data from space and getting it cleaned up, organized, and even simplified. So the very first step in this boot camp was all about simplification. I mean, the original data set had 14 super specific, really complex categories. We're talking different types of supernovae, tidal disruption events, kilonovas, the whole shebang. That's a lot to learn all at once. So to make the task manageable for the AI, the researchers just grouped all of those into the 5 broader personality types we just talked about: S-like, long, fast, and the rest. But this simplification step immediately uncovered a huge hurdle. The dataset was really imbalanced. As you can see, there were just way more S-like examples than anything else. And this is a classic problem in machine learning. If an AI sees one type of thing over and over and over again, it can develop a bias. The easiest way for it to get a correct answer is to just guess the most common thing every time, right? But that's not real learning, that's just lazy. Okay, the next step in bootcamp was to standardize everything. See, not all the light curves were the same length. Some had way more observations than others. So the researchers used this technique called padding. It's pretty clever. They basically just added filler values to the shorter data streams until every single object, every single one, had exactly 352 measurements. Now the AI has a perfectly uniform input to work with. No more apples and oranges. Part 4, the AI's report card. All right, boot camp is officially over. Our AI has studied all that simplified, standardized data. So now it's time for the final exam. This is the moment of truth. How well can it classify a totally new set of light curves it's never, ever seen before? Let's take a look at its grades. And the results are, well, it's kind of a mixed bag. So the main score here is something called an ROC-AUC score. All you really need to know is that a 1.0 is a perfect score, and a 0.5 is basically just random guessing. And as you can see, it absolutely crushed it on the S-like and periodic objects. Got an A+ and an A, with scores of 0.95 and 0.99. I mean, that's incredible. But the bad news is its performance on those rare, long, and fast types was not great. It barely scraped by with a D. So it totally aced the subjects it studied the most, but really struggled with the trickier, rarer stuff. Which brings us to Section 5, the early detection test. So look, our AI did pretty well on its final exam when it had the full picture. But here's the thing. In the real world, astronomers need to know what something is, like, right away, not weeks later after it's already faded. And that brings us to a much, much harder challenge, the early detection test. So yeah, this is the real million-dollar question, isn't it? Can AI actually make the right call with just a tiny glimpse of the data? I mean, what if it only has 5 days of data, or 10, or 20? Can it figure it out with just a small fragment of the whole story? And the answer was a hard no. It couldn't. Not even close. The AI's performance totally collapsed. You can see right here, the less data it had to work with, the worse its accuracy got. And its number one mistake? It just started misclassifying almost everything as slick. Remember that bias we were worried about from the imbalanced data? Well, it came back to bite them hard. As soon as the AI got uncertain, it just fell back on the one answer it knew best. It defaulted to its comfort zone. So let's wrap this up with part 6, smarter AI, better data. Now, this whole early detection thing might sound like a total failure, right? But actually, this is where the real learning happens. The AI's successes, and maybe even more importantly, its failures, gave the researchers a perfect roadmap for what to do next, to build an AI astronomer that actually works in the real world. So here are the big takeaways from the whole experiment. The limitations were crystal clear. First, that class imbalance created a huge bias. And second, the AI just wasn't good at spotting those short, sharp peaks in the fast and long objects. So the solutions kind of rate themselves, don't they? You have to use techniques to balance the data better. You need to pre-process the data to really highlight those critical first moments of detection. And hey, maybe it's time to explore even more advanced AI, something like transformer networks. And that really leaves us with one last big thought to chew on. This whole process just goes to show you that an AI is only ever as good as the data and the instructions that we give it. So as we get ready for this insane new era of cosmic discovery, maybe the real challenge isn't just about building a smarter AI. Maybe it's about us learning how to be smarter teachers.